do 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 do. Yay, we reached the finish line. But how many ways are there to reach the finish line? We'll explore that in this video. How many ways to go from 0, 0 to 5, 6? Is you can't visit all of 1, 2, 3, 4, and 5, 5. Because there's a monster that will eat you if you visit all 3 locations. So you can visit 1 or 2 of them, you just can't visit all of them, because then the monster will eat you. So, how should we do this? Interesting. So, to do this, we'll need to use path counting. So first, let's just find the number of ways to go from 0, 0 to 5, 6. This itself is a problem of its own. 5, 6, right? So this is a standard path counting trick. And this path counting trick is used on many AMC 8 problems, so it's definitely really good to know. So essentially, we're trying to go from 0, 0 to 5, 6. And we must move right or up on every move. So we can't move down or left, just to make a clarification. You have to move right or up on every move. You can't just keep going up, down forever. So how many ways are there to go from 0, 0 to 5, 6? We can take down all the cases, but that's going to be really long. Is there a cool trick we can use? Well, let's just take a look at a sample path, okay? Right, then up, then right again, then up, then right, and then up. That's a sample path, a perfectly valid one that you can take. Well, what if we wrote the rights as R's and the ups as U's? So R, U, U, then R, U, R, 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 U, U, U. Interesting. Sequence of letters. Oh, but what if we have a different path? Let's say this time we go up, and then right, up, right, and then up. U, 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 R, U, R, U, R, 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 U. Another perfectly valid sequence. But it seems like this is just a rearrangement, right? Oh, what if the number of ways to get from here to here, moving right or up, was just the number of rearrangements of a sequence of R's and U's? Indeed, that is true. So if we have 5 R's and 6 U's, the number of ways from going from 0, 0 to 5, 6 is just the number of ways that we can rearrange the letters in this word. Because every sequence, if it's a R, right, U, up, R, right, U, up, whatever it might be, it will take us to the finish line at 5, 6. So, how many ways are there to rearrange the letters of this? There's 5 R's and there's 6 U's. 11 total letters. And we have to choose 5 of them to be R's. So 11 letters, you can imagine 11 slots. Or maybe an easier way to think about this is word rearrangement formula. 11 factorial by 5 factorial, 6 factorial. And this is also the same thing as 11 choose 5, because we can think of having 11 slots and then just choosing 5 of them to be R's, right? 11 factorial over 5 factorial, 6 factorial. Let's simplify this. We can rewrite it as 11 times 10 times 9 times 8 times 7 over 5 factorial, 120. This right here is 720, so we can cancel it out to get a 6. That's 42 times 11, 462. But there's a constraint in the problem. You cannot visit all of these locations. You can visit 1 or 2 of them, just not all of them. How should we do this now? Interesting. we can use complementary counting, which we learned in the previous video. Complementary counting, remember, is where we find the total number of possibilities, which is this right here, and subtract the ways where the constraint is, where the opposite of the constraint happens. So where we do visit all the points, those are the bad ways which we will subtract. Okay, that's interesting. Let's do that, I guess. So 1, 2, 3, 4, and 5, 5. Let's graph those on our graph. Okay, so 1, 2, that's going to be right here. 3, 4, that's going to be 3, 4 will be right here. And 5, 5 will be right here. Okay, so a monster will eat you if you visit all 3 locations. You can not visit all 3 of them, but we're doing complementary counting. So how many ways are there where you visit all 3 of them? To do this, notice how we can just say that find the number of ways to go from 0, 0 to 1, 2, then find the number of ways 1, 2 to 3, 4, then 3, 4 to 5, 5, 5, 5 to 5, 6. And that will be, if we multiply them together, the number of ways to go from 0, 0 to 5, 6, assuming that we have to visit these points. Because if you can think about it, each one of these is just their own grid of their own. It's just their own grid. And by the way, we can also derive a formula. The number of ways from 0, 0 to mn, moving only up and right, is m plus n choose m, right? In this case, it was 6 plus 5 choose 5. And so we can think about having each of these small little grids. And what we must do is just go find the number of ways from here, go from here to here in this small grid. And this small grid has R, U, U. So that's going to be just 3 ways, because there's 3 choices for where the R can go. So 3 choices to go from 0, 0 to 1, 2. Now what about from 1, 2 to 3, 4? Well, this is a 2 by 2 grid, and that's going to be R, R, U, U. And that's, well, we can use the formula, or we can just see that this is 4 choose 2, because we have 4 slots for the R's and U's, and we choose 2 of them to be R's and 2 of them to be U's. 4 choose 2 is 4 times 3 divided by 2. That's 6. Now, 3, 4 to 5, 5. For this, we must have 2 R's and 1 U. So R, R, U. R, R, U. Well, there's 3 slots. We choose 1 of them to be U. That's 3, choose 1, which is 3. Now what about from 5, 5 to 5, 6? That's just 1, because we have to go up. So just 1 here. So we multiply all these together to find the total number of ways from going from this point to this point, assuming we must pass through all of these intermediate points. So the number of ways to do that is just 3 times 6 times 3 times 1, which is 54. So remember, we're doing complementary counting. This was the total number of ways, and this is the number of ways that do not satisfy this condition. So 462 minus 54, 408. And that is our answer. Let's recap. So first we found the total number of ways using the path counting trick. That was 462. Then what we did is we found the number of ways that did not work, which was 54. And by doing that, by looking at each of the intermediate grids. And we subtracted that off to get our answer, 408. Let's take another really cool problem, path counting. Sally is inside a pen consisting of points A, B, such that 0 is less than or equal to A is less than or equal to B is less than or equal to 4. Let's draw that. 0, 0, and 4, 4. Let's just draw a nice little grid. So the condition in this problem is from point xy, she can move to xy plus 1, xy minus 1, or x plus 1, comma y. Okay. So this is interesting. This is not like our standard problems. If we were to model our standard problems on the coordinate plane, they would look something more like xy. This is our standard path counting problem. We can go right, which is x plus 1 comma y, or up, x comma y plus 1. But this isn't our standard path counting problem. This is unique and it's very special. Okay, so the key idea for this problem, let's just look at a few cases. Whenever you're stuck on a tricky problem, just play around with it, see what happens. You'll discover a pattern maybe, and that's exactly what we'll try to do here. We have no idea what's going on yet, so let's just see, So what is this first thing? It says x to y plus xy to x plus y, x comma y plus 1. And that just means increasing the y coordinate by 1 or moving up. So that's analogous to up. It's much easier to deal with U's, D's, and R's and L's for up, down, left, right than these complex coordinate notation. The other case is xy to xy minus 1. And that is going down, right? Decreasing the y coordinate by 1. So up, down, and x plus 1 comma y. That's just increasing the x coordinate by 1. That's right. So now up, down, right. Okay, that seems a lot easier to handle. So 0, 0 to 4, 4. So this is very similar to our path counting problems, except now we have got a down. Okay, and another thing, she cannot revisit any point she has visited before. Oh, and this is going to be the key to solving our problem. Okay, like we said, let's play around with it a little bit. First, let's say we move up. Okay? Or if we move up, we can, let's say we end up here. What can we do? We can move right, of course. That's one possibility. Can we move back down? The answer is no. We can't move back down. Why? Because we've already visited 0, 0, right? That's where Sally starts. So if we move back down, that would be violating the condition. That's not allowed, so we're going to have to look at some other possibilities. So down is not possible if Sally already moves up. Can Sally go up again? Of course. There's nobody. Sally has not yet visited this point. Okay. Now from this second point, let's say Sally reaches this second point. What can Sally do? Again, can't go down because this point has already been visited, but can go right or up again. Same thing. From this point right here, Sally can go right or up again. And if Sally reaches this top point, then really there's only one choice, right? Just right. Also in the beginning at 0, 0, Sally could have gone right straight away. No need to wait for all the ups, right? Just go right straight away. Okay, this is getting confusing, right? How many different possibilities are there? So we can either go right straight away, or we can go up and then right, right? That's one possibility. Up and then right, or we can go up 2 times and then go right. So up, up, right, or even 3 times and then right. So up, 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 right, and finally we can go up 4 times. And after we go up 4 times, we're forced to go right because we can't go back down to an already visited point, and we have to go right. There's nothing above here, right? It's 0 less than or equal to a less than or equal to b less than or equal to 4. All that means is that it has to be within this 4x4 grid. It can't be like, we can't just keep going up however much we like till infinity. Okay, and after that, of course, there's a right. As you can see, there's 5 possibilities here. Okay. Now let's say Sally ends up in the second column somewhere. Now what? Okay, this is going to be a little bit more tricky because now Sally could be at any point. Sally could be here, 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 or even here. So let's just take one case. What if Sally ends up going up 2 times and then going right? That's one possibility, right? Okay, so in this possibility, how many different ways are there to go from here? Up, down, or right are our 3 possibilities. So one possibility, so this is the first move. Let's now look at the second move. Let's see the different color. So second move, of course we can either go right straight away. That's definitely a possibility. Or we can go up 1 time, and then let's say we end up here. From here we can go back down because this point is already visited. We can go right from there, so up then right, that's one possibility. Or we can go up 2 times and then go right. Right? After we go up 2 times, we can't go back down because of the visiting condition, and we're forced to go right because that's the only move possible. Up, up, right. Now, in this case, we can also move down, right? Because there's nobody, Sally has not yet visited this point. So Sally can also go down. So Sally goes down. Down, and then maybe Sally goes right from here. So Sally can go down, right. Another possibility, down, down, right. Okay, so it seems like there's again 5 possibilities. Oh, but we don't know it's 5 yet because we just took any random point. Sally does not necessarily have to be here. Sally instead could have maybe reached, let's see. Let's say instead of reaching the 3rd point in the 2nd column, Sally reaches here. So if Sally reaches here, what are the different possibilities? So again, we can either go right straight away, we can go up, then right. We can go up, up, right. Or we can go up, 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 and then right. And again, we can't, after we go up, we can't go down because that's already visited. Similarly, after we go down, we can't come back up because that's already a visited point, right? The condition, she cannot revisit any point that's already been visited. Oh, this is not the 3rd move, sorry. This is 2nd move, a different case. And in this case, we can also move down right. Again, 5. Is it? It's seeming like for the 2nd move, there's always going to be 5 ways. And that's indeed true. Why? Because on this point, we can either move right straight away, or by going up or down, we can go to any other point in the column. So we can go to any other point in the column. So that's going to be, well, you go right from this point, or you go to any of the other 4 points and then go right. That's 1 plus 4 ways. That's 5 total ways. So it seems like no matter what, there's going to be 5 ways for the 2nd choice. Similarly, no matter which point we land down in here, there's going to be 5 ways to go here. 3rd, also 5. 4th, also 5 ways to go to the 5th column. Here. And this is where the final step is. From here, we can't just go however we like. We're not trying to go right this time. This time, we have to go to 4, 4. We have to go up. So whichever position we land on, the idea here is all we have to do now is up, 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 up. We don't want to go, we can't go right, of course, there's nothing there. And let's say we end up here. If we go down, then we're going to have issues because we can't go back up if we go down. We basically blockaded ourselves. We've blocked ourselves from reaching the destination because you can't visit this point again after going down. So going down is definitely a no-no. So we have to go up. So no matter what, wherever we land on, the idea here is just to go up, up, up until you reach 4, 4. And there's actually only one way to do that. Because wherever Sally lands, there's just one way to go up, right? A sequence of U's, there's no rearranging or anything. We can either go up 1, 2, 3, 4, or 5, or even 0, of course. So the answer is just 5 times 5 times 5, and that's 625. That's a really brilliant problem that utilizes careful observation and pathfinding, of course. Okay. Now let's look at our final problem from the AMCA. A game board consists of 64 squares that alternate in some color from black and white. The figure below shows a square P in the bottom row and a square Q. A step consists of moving a marker onto one of the adjacent white squares above. How many 7-step paths are possible? So before we explore this problem, let me show you a nice cool trick. So we just learned that, of course, the pathfinding formula, if we were starting here and we were trying to end up here, the number of ways is, well, you have to go right 2 times and then up 2 times. It was 4 slots, choose 2, 4 choose 2, which is 6. Now here's another cool solution, and this is like a DP method if you know programming. So what we can do here is, how many ways are there to get to this point? 1, right? We just go like that. There's just one way to get here, because we're starting here going right and up, of course. There's just one way to get to here. Similarly, there's one way to get here. We are at the starting point and we just go up. Now, how many ways to get here? So to get here, we move up from here, or move up from here, move right from here. That's 2 ways. What about how many ways to get here? So to get here, we have to just go right from the second point. Since there's only one way to get here, there's also just going to be one way to get here. We just move right from this point. Similarly, there's going to be one way to get here. We just move up 2 times. There's one way to get to this point here, and from there, you must move up to get to this point here. There's just one way. There's no other way to get to this point. Now, what about this point over here? How many ways to reach it? So, there's 2 ways to reach here, 1 way to reach here. So, we can either move up from here or right from here. There's a total of 2 plus 1, 3 ways to reach here. Similarly, to get here, we either move up from here or right from here. Again, 3. And to get to the final destination, there's 3 ways to get here, 3 ways to get here, a total of 6 ways to reach the final point. We got the same answer. And this method is really cool, because sometimes if you have constraints like, for example, let's say you can't go to this square is blockaded. Now, we just say this is 1, 2, 3, and instead now, we can just see that the number of ways to get to the final point is just 3, because we have to move right. This square is blockaded. And this kind of method is very useful. We'll use it to solve this problem over here. Okay, so just to remember what the problem is, we're going from P to Q. Let's clear the page. We're going from P to Q, and basically we go from a white square to an adjoining white square. So essentially over here, we have 2 possible moves. The first move is right up. The second move is left up. Both of these are perfectly valid moves, because we're going from white to white. So let's use our method. There's only going to be one way to get here, right? We go directly from the start. there's going to be one way to get here as well, right? Similar. So then how many ways are there to get here? So from this location over here, there's just one way to go here. And that's the only way to get here. So that's again one way. Now what about this location over here? There's one way to get here, one way to get here. So there's 1 plus 1 equals 2 ways to get to the square here. So 2. There's 2 ways to get here, 1 way to get here. So there's going to be 2 plus 1 equals 3 ways to get here, right? Okay. Oh, and also, by the way, there's going to be just one way to get here. We just go diagonally like that. Now, how many ways are there to get here? Again, 2 plus 1. There's 2 ways to get here and 1 way to get here. That's 3. And there's also going to be 3 ways to get here, right? There's no other possibilities because this is the only white square that's underneath. Okay? And we have to go from the row above to the row above. So we go from here to here. And there's no white square here, so we can't go from there, of course. Now what about to get here? That's just 3 plus 3, 6, right? There's 3 ways to get here, 3 here. Add them up, 6. Cool. Now, what about this square here? That's just going to be 3 because there's no ways to get, or actually, never mind. Because there's one way to get here, there's also going to be one way to get here. We have to just keep going diagonally in this direction. We can't go from this square. So therefore, the number of ways of getting here are going to be 3 plus 1 equals 4. Right? Not 3, sorry. Because there's one way to get here, indeed. So then, how many ways to get here? That's just 4 plus 6, 10. Because there's 4 ways to get to this square, 6 to get to that square. Add them up, 10. Now, here, 6 ways to get here, 3 here, so 6 plus 3, 9 ways to get here. Okay, now we can keep extending our line of ones. There's going to be one way to get to any square in this diagonal because we just keep moving in that diagonally direction. So the number of ways to get here, just 4 plus 1, 5. The number of ways of getting here, that's just 15 by just adding up 5 and 10. The number of ways of getting here is 10 plus 9 because we come from any of these bottom 2 squares, 19. And we're trying to reach Q. And there's also going to be 9 ways of reaching here because we just have to go move that way. We can't come from this square. There's no square here. So the number of ways of reaching Q is just 19 plus 9, 28. So 28 is our answer. Our simple but a straightforward way, yet still a very clever trick. Okay, this is a little bit tedious and a little bit bashy, so now let's explore the complementary counting solution. Okay? So notice here, let's clear. So notice here, 7 moves, right? And like I mentioned earlier, left up, right up. And there's 7 different moves. Oh, but notice here, we're going right 1 square. At the end, it's up. At the end, we're going up 7 and right 1. 7 step paths, and each step is left or right. What does that mean? So at the end, if we're trying to net going 1 square right, we must have 4 right jumps and 3 left. Three left. So how many ways are there to do this? Our same trick. We can write them as R, 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 L, L, L. 723 equals 765 over 6, that's 35. This is the total number of ways. But be careful here, not all of these ways actually work, because they can go off the grid. For example, something like this would work if the grid was large enough, but it isn't large enough, so something like this wouldn't work because there's no square here. So we have to somehow subtract these methods, subtract these cases using complementary counting. How should we do that? First of all, when will it even be outside the grid? The key here is that P is over here. So as long as you don't move more than two, as long as you're never more than 2 right of P, you won't be off the grid, right? If you're 1 right of P, you'll be somewhere here. If you're 2 right of P, you'll be somewhere here. But if you go 3 right of P, so let's say you go here, then here, you're outside the grid. And notice that we are counting these cases here because right, we're counting that case. It's an extra extraneous case we must subtract. So essentially, if we are 3, or we can even be up to 4 right, so if we're 3 or 4 right of P, the initial position, not good, bad case. We must subtract. Let's take them separately. Let's say we're initially, how many ways to get 4 right? So how many ways, how many invalid paths are there where we're 4 right of P? R. That's definitely a way where we're outside the grid, right? Because R takes you here, then another right, and by R I mean right up, just to be clear here. Right up, right up, right up, right up. And we need 4 right up jumps anyway. So 4 of them will take you way outside the grid. So any kind of combination with R at the beginning doesn't work. And from here, the only possibility is this, because we must have 4 R's and 3 L's. The 3 L's will come last then, and this is one way that doesn't work. So let's just make it clear here. Ways that don't work for doing comp counting. Now we don't have to be 4 right of P for it to be an invalid case. We can also be 3 right of P. So 1, 2, 3. If we're 3 right of P, that also fails. What are the possibilities for that? R. And from here, we've got 1 R left and 3 L's left. The number of ways of arranging those is just, there's 4 letters and we choose one of them. That's 4. So there's 4 ways here. But be careful here because we've already counted the case where R is at the beginning. If we have R, L, that's already counted. So we're looking at the case where only 3 R's are at the beginning, not 4. And that is just 4 minus 1, 3. And those include cases like this, or like this, where we have R, then some lefts, then some right, then the right again, the last right, and then some more lefts after that. But we don't necessarily have to have a sequence of R's at the beginning to go 3 right. Another possibility is we can have 4 rights and a left. Because even if we go left in the beginning, 4 rights will still take off the grid. Because at the end, that's net 3 right. 4 right minus 1 left. That's net 3 right, which is off the grid here. So these cases, anything that starts with some combination of some permutation of this, fail. So what are those possibilities? Now I'm just going to write these out because this is a problem where we could have some overlap. L, R, L, R, 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 L, R, R, or R, 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 L, R, or R, 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 L. These are all the possibilities. We could have just said, oh, there's 5 choices for where the L can go. But the reason we have to be careful here is because we've already counted a lot of these. We've already counted this case, right? 3 R's at the beginning, so we can cross that out. And we've already counted this case, 4 R's at the beginning, cross that out. How many ways for the rest of these cases? So no matter which 5 start in the beginning, 4 R's, 1 L, because we only have 4 R's total and 3 L's total, we must have 2 more L's at the end of each of these. And there's really no ways to permute that, so just 1, 1, 1. So in total, 1 plus 3 plus 1 plus 1 plus 1, that's 7 ways fail. So the answer, 35 minus 7, 28, and we're done. So the key thing here was first looking at the pathfinding method and noticing a little bit different. Now it's not just R's and L's on a square flat grid, it's L up, R up. So we found 35 ways by using our path counting formula. But then there's some cases that don't work. And to do that, we see that we must be 3 right outside the grid, or even 4 right outside the grid. We look at those cases. You could just manually write them out if you really wanted to, which we kind of did at some points as well, just to be careful here. But the key thing was not to make sure you didn't have any overlap, because there was a lot of overlap between these cases, as you can see. We subtracted off those cases to get our answer. Okay, so next we're going to talk about a really cool combinatorics technique, recursion. And this is personally my favorite technique because you know what it allows you to do? It allows you to make a super complicated problem for such large numbers into a problem for like 1 or 2 numbers. And that's what makes it really cool. We'll look at that in the next video. You can check it out right there.